Very good morning, all of you. Today's topic of discussion is matrix 10 multiplication algorithm. So to understand matrix 10 multiplication algorithm, let us first solve one numericals on matrix 10 multiplication. And with reference to the solution of the matrix 10 multiplication problem using dynamic programming, we will derive the algorithm from the step-by-step solutions. And if we refer the solution at the time of constructing the matrix 10 multiplication algorithm, it would be very easier for us to design the algorithm of matrix 10 multiplication problem. So let us now go for solving one sample problem of matrix 10 multiplication. So before considering a numerical, let us first understand some important part of this topic, some important section, and the meaning of some important terminologies. Suppose we have two matrices. Name of the first matrix is A with the dimension 2 cross 3, and the name of the second matrix is B with the dimension 3 cross 4. It is observed that total number of columns of A is 3, which is same as total number of row of the second matrix B. So we can multiply A into B in this order. And suppose the resultant matrix is C, obviously the dimension of C will be 2 cross 4. There is no doubt. Everybody can understand it. Then, just for a brief illustration, A looks like this. A has 2 rows and A has 3 columns. Similarly, B looks like this. B has 3 rows and B has 4 columns. Okay. And C looks like C. It has 2 rows and it has 4 columns. So if I concentrate on C, the total number of elements in C is actually 2 cross 4. That means every row of C consists of 4 columns, that is 4 elements. So C has 2 rows total. Each and every row consists of 4 elements. So altogether it is 2 cross 4, 8 elements present into C. Now we should know to get the first element of C, how many multiplication is required. We just focus on the total number of columns of A. There is 3 columns. And total number of rows of B, there are 3 rows. So to get the first element of C, we need to multiply first row, first column element of A and first row, first column element of B. This one and this one needs to be multiplied. Plus this one and this one needs to be multiplied. Plus this one and this one needs to be multiplied. So after 3 multiplication and summation, we are getting the first element of C. So here, if we focus on the number of multiplication, this is the first multiplication, second multiplication, third multiplication. So altogether 3 multiplication is required. So we can say that to get total 8 elements in C, we need total 3 multiplication for each element of C. 3 multiplications for each element of C. So to get this, the first element in the first row, first column of C, it needs 3 multiplication. The same logic is applicable for the second element, that is first row, second column element of C. It again needs 3 multiplication. So if we calculate the total number of multiplication required to get C, which is of dimension 2 cross 4, actually it will be 2 cross 4 into 3. Because each and every element needs 3 multiplication and altogether it is 8 elements. So 2 cross 4 it is 8 into 3. So altogether 24 multiplication is required. And this is actually called the cost of multiplication. Cost of multiplication. Sometimes it is called scalar multiplication. And in the matrix 10 problem, we are basically interested on the cost of multiplication. We are least bothered about the element present in C. Rather, we are mainly focusing on the cost of multiplication to obtain C. It is a very simple concept. So how this 24 comes, we got the logic. But if the dimension of A and B is given, the same value, that is 24, can be easily obtained by multiplying this one common one once, that actually symbolizes the number of multiplication for each element in the resultant. Then the last one, so if you multiply them, 2 cross 3 it is 6, 6 cross 4 it is 24. You are getting the same value. So the logic that we have discussed to get 24, I think it is now clear. That is actually called the cost of multiplication. So similarly, if we have two matrices A and B with the dimension 3 cross 4 and 4 cross 5, we can easily calculate the cost of multiplication of C, which is of having the dimension 3 cross 5. Actually, the cost of multiplication will be 3 into the common one once, that is 4, then the last one, that is 5. So it is actually 3 into 4, 12 into 5, which is 60. Okay. So now, if the matrix chain, here the chain means we have two matrices as an input to get the product. Here, if we consider this is as a chain of matrices, here in the chain of matrices, there are two matrices. So the conclusion says we are least bothered about the product. We are mainly interested about the cost. And if we are mainly focusing on the cost of multiplication, which is also called the scalar multiplication value, then we must know how to multiply the matrix chain. That means in which order we have to proceed further. So now let us assume that I have three matrices in the chain. So just before some time I've told that if I consider this is a chain of matrices, here the chain consists of two matrices. Assume that I have a chain of matrices where total number of matrices is 3, A1, A2, and A3. And assume that they have the dimension of 2 cross 3, 3 cross 4, and 4 cross 5. So nobody can give any or throw any objection that they cannot be multiplied in that order. Yes, they can be multiplied in this order because there is a match. That is the total number of columns of A1 is same as the total number of row of A2. And there is also a match. Total number of a column of A2 is same as the total number of row of A3. So there will be no misarrangement of the order, so we can multiply them. But the way we can multiply them is now a big question because we are least bothered about the product. We are only focusing on the cost of multiplication. So our main concept now comes to the section. The way that we can multiply them is a big question. So the way that we can multiply them is a big question, there is no doubt. So we use the concept of parenthesization of the matrices. That means if I apply the concept of the parenthesization of the matrix chain, then it looks like I have three matrices in the chain. The way that I can parenthesize them is nothing but 2. That means I can keep A1 separately. Then I focus on multiplying A2 and A3 first. Okay, let me put the sign of multiplication here for better understanding. So this is the way that we can parenthesize in one way. That means A2 and A3 should be multiplied first, because we know in case of simplification, the parenthesis is of having an importance. If we parenthesize one portion of the expression or the equation, that part needs to be solved first. So here the same concept is applicable. So after the first matrix, we parenthesize them, second and third matrix together. Another approach is very simple to understand. We multiply A1 and A2. That means we give the parenthesis in between to cover A1 and A2. Then the resultant needs to be multiplied with A3. Then the question is, sir, is it possible to get the same result? Yes, you will get the same result because A1 separately having the dimension 2 cross 3. Here A2 is of having the dimension 3 cross 4 and A3 is of dimension 4 cross 5. If you multiply A2 and A3, suppose the resultant matrix R1 is of the dimension obviously 3 cross 5, okay, then you take A1. A1 is of dimension 2 cross 3. R1 is of dimension 3 cross 5. So the final matrix R will be of dimension 2 cross 5. There will be no issue. And same thing, if the intermediate result, that is A1 and A2, R1 is the intermediate result of multiplication of A1 and A2. A1 is of having 2 cross 3 dimension, A2 is of having 3 cross 4 dimension. So R1 should be of having 2 cross 4 dimension. Then I take A3. A3 is of having the dimension 4 cross 5. So if I'm sorry, let me go back. So if I multiply R1 and A3, the resultant matrix, suppose it is R, it should be of dimension 2 cross 5. So there will be no issue that I'm getting the different result. No, I'm not getting the different result. Every time I'm getting the same result, that is the resultant matrix R is of having the dimension 2 cross 5 in both the cases. But the question is, as we are least bothered about the product, we are mainly interested on the cost of multiplication. Let us now calculate the cost of multiplication. In the first case, that is the first approach, the cost of multiplication is calculated as, we are multiplying A2 and A3 first. So R1 is the resultant. So for R1, the cost of multiplication is nothing but 3 into 4 into 5, applying the same concept here. 3 into common 1 into 5, that is 3 into 4, 12, 12 into 5, it is 60. Then I have R1 with dimension 3 cross 5 and A1 with the dimension 2 cross 3. Then A1 into R1, the cost will be 2 multiplied by 3, 3 is common here, into 5, that is 2 cross 3, 6, 6 cross 5, 30. So altogether it is 60 plus 30, then it is 90 actually. So the cost of multiplication for the first case is simple 90. Then you come back to the second combination, second case, where I am calculating A1 into A2. A1 is of the dimension 2 cross 3, A2 is of the dimension 3 cross 4. The resultant R1 is of the dimension 2 cross 4. So what is the cost? Cost is nothing but 2 into common value, that is 3 into 4, that is 2 cross 3, it is 6 into 4, 24. Now focus it. We have R1, that is 2 cross 4. We have A3, that is 4 cross 5. So the cost of multiplication is 2 into common 1 once, then into 5. That is, if I'm not wrong, 4 into 5, 20 into 2, that is 40. So 24 plus 40, altogether it is 64. So the total multiplication for the second case, it is 64. So if we get the same result, that is R, with the dimension 2 cross 5 in both the cases, and we are getting different values of the cost of multiplication. In the first case, it is 19, the second case, it is 64. So why shouldn't we go for the minimum cost of multiplication? If I get the same result in both the cases, that is R with the dimension 2 cross 5, so why should we put extra effort? We shouldn't put extra effort. We have to go with the combination of the multiplication where the cost is minimum. So that was our main objective. We are least bothered about the product. We are mainly interested on the cost of multiplication, and we will go for that cost where the cost is actually minimum. So this is one of the optimization problems under dynamic programming paradigm. So here we are mainly interested on to multiply chain of matrices, but we are least bothered about the product. We have to have the concentration on the cost of multiplication rather the minimum cost of multiplication. So if the chain becomes lengthy, here in the initial case, the chain consists of only 2 matrices. Very simple to understand, very simple, no headache here. We increase the chain length with the extra 1 matrix, that is A1, A2, and A3, the chain is increasing. So in the similar way, the chain may be increasing A1, A2, A3, A4, A5, and so forth. So there are a number of ways you can parenthesize the chain. But the problem is how to keep track, because not all possible solutions to be generated and go for the minimum one. It is not at all a feasible solution. So you must have to generate a formula by which, though the chain becomes lengthy, you can solve the problem. Though the chain becomes very lengthy, you can also solve the problem if you derive one formula and you can apply the formula for all length of the chain. That means the chain becomes lengthy, chain becomes a medium length, chain becomes a short length, whatever it is, doesn't matter. So today, as our main focus is to discuss the algorithm, so we just assume that my students knows it well that how the formula can be established. So assuming that we know the formula of the matrix and multiplication, because if the chain becomes lengthy, it is not possible for a human being to understand the way that you can parenthesize the chain. It is very difficult to keep track, because if the chain consists of 4 matrices, there are a possible number of the number of ways that you can parenthesize the matrix chain is increasing. So again, I'm telling it is not possible, not all possible solutions to be generated and go for the minimum one. Identification of the minimum one from all a good number of all possible ways to solve of the parenthesization is become very tedious job. It is not possible. So that's why we should be focusing on to establish the formula of matrix chain multiplication. And as this class is not focusing on the way that we derive the formula, so for the time being, we assume that my students knows the formula. So the formula of the matrix chain multiplication problem I'm going to write. But before that, let us understand one very common thing, assuming that the students knows it. But to write the algorithm, it is my responsibility to explain all the parameters which is required to know before we write the algorithm. So here a very simple concept we must know, like the way that we go for solving the cost of multiplication formula, how this 24 came. So this was the logic, I explained it. And if the dimensions are given, how 24 can be obtained from here also you understand. So the same way, let us go for the second part of the discussion that we must know here. So suppose you have 4 matrices, A1, A2, A3, and A4. And suppose the dimensions are 2 cross 3, 3 cross 4, 4 cross 5, and 5 cross 6. So here, if the chain is not given, rather the dimension sequences are given. If somebody says that, assume that you have the sequence of dimensions like 2, then 3, then 4, then 5, then 6. Then you must have to guess that how many matrices are present in the chain. As the matrices are not explicitly given like this, somebody may supply the sequence of dimensions only, dimension sequence. So if the dimension sequence is given, anybody can guess the total number of matrices present in the chain. So first of all, count the total number of dimensions given, 1, 2, 3, 4, and 5. So altogether 5 dimensions are given. So if the total number of dimension sequences given is 5, the number of matrices in the chain would be total number of dimension minus 1, which is 4. So how can you get it? The first 2 is the dimension of A1. Second and third is the dimension of A2. Third and fourth is the dimension of A3. And fourth and fifth is nothing but the dimension of A4. And here you can easily guess row column relationship still persists. Okay. As the order of the matrices must preserve the row column relationship before multiplying them. So from this concept, it is very easy to understand that if the dimension sequences are given, total number of dimension sequences given, if it is 5, 6, whatever it is, that figure minus 1 will ultimately reveal the total number of matrices present in the chain. So we can say that if n be the total number of matrices in the chain, it is actually p dot length minus 1. So what is p actually? P nothing but the sequence of dimension. Here it is p. P is nothing but the sequence of dimension. P is actually nothing but an one-dimensional array to hold the dimension sequence. That is by programming we can say. So P is nothing but the dimension sequence. So P dot length actually count the total number of dimensions present in the array or present in P. So actually this is the formula. Total number of matrices is nothing but dimension dot length, total number of dimensions actually minus 1. So P dot length minus 1. So it is actually number of dimension present, which is nothing but called P dot length. P is the dimension sequence representative. So it holds the all dimensions. So actually it looks like an array. Actually it is really an array. Whenever you do the programming, you consider P as an array, one-dimensional array, which is responsible to store all dimensions. And if you calculate the length of P, that length minus 1 actually reveals the total number of matrices. This is very simple to understand. Another issue is, suppose you have this matrix A1, okay, 2 cross 3, fine. So actually we call the dimension of A1 is expressed as P0 into P1. If second matrix is A2, its dimension is 3 into 4, its dimension should start from P1 into P2, like this. We follow this convention. So if I have the matrix AI, its dimension should be Pi minus 1 into Pi. This is very vital concept. This is very important part for algorithm design, and be careful about it. If you have the matrix with the dimension such and such, you must identify the index of the matrix, that is A1 or A2. Its dimension should start from its index minus 1 into its index. That means P0 into P1. So here it is very clear now that P holds all the dimension in such a way that here it is 2, that is 3, that is 4, that is 5, that is 6, as per the example. So it is actually P0, it is actually P1, it is P2, it is P3, and it is P4. So P0 into P1, that is for A1, P1 into P2, that is for A2, P2 into P3, that is for A3, and P3 into P4, that is for A4. In this way, you can consider or construct P, that is holding the dimension sequence. Okay, so this is about. So for a particular matrix AI, ith matrix, its dimension should be Pi minus 1 into Pi. Okay, so this two you must know. That is total number of matrices is nothing but P dot length minus 1. And if you have a particular matrix AI, its dimension should be Pi minus 1 into Pi. So this is what about actually. So now let us consider one problem, and let us go for the brief solution of the problem. So before that, okay, first of all, let us consider one problem, A1 into A2 into A3 into A4. We have 4 matrices with a very simple dimension, 2 cross 3, 3 cross 4, 4 cross 5, 5 cross 6. So this is actually P0, this is P1, this is P1, this is P2, this is P2, this is P3, this is P3, this is P4. Okay. So total number of matrices is P0, P1, P2, P3, P4, total 5 dimension minus 1, that is 4, and it is visible also from here. So now the formula which I am now not going to derive. So in the chain, if the chain is represented, here the chain is A1, then A2, then A3, then A4. I'm not using different parameter for representing the matrices because I'm using A1, then A2, then A3, because it will be required to establish the algorithm. So in the chain, actually it looks like the first matrix is AI, second matrix is obviously AI plus 1, A1, A2, I plus 1. Then the chain ends at suppose AJ. So here it is j. Okay, 4 is j. The recursive definition, if the chain is given, the recursive definition for minimum cost of parenthesization. Actually, you have to identify the way that we go for multiplying the matrices, and that can be done using the set of parentheses we can place to identify the section which we needs to be multiplied first, then go for the remaining part, etc., etc. So actually the parenthesis plays an important role here. The recursive definition for minimum cost of parenthesizing the product of the chain AI plus 1 up to aj becomes m of ij. M is a table that my students knows it. M of ij equals to 0 if the chain consists of only one matrix, because for a single matrix there will be no multiplication cost. So if I equals to j. So if I equals to j, then you have only one matrix. Okay. So for one matrix, there will be no cost of multiplication. Otherwise, you divide the problem into sub-problem. This is the basic concept of the dynamic programming. But it is not like divide and conquer. Here you have to divide the problem into sub-problem where the sub-problems are dependent on each other. Okay. And once you can solve the sub-problem and you store the sub-problem, that solution may be required in future to get the solution of another sub-problem and so forth. So actually, we are dividing the chain as the chain is symbolized at AI plus 1 up to aj. So at the position k, you can divide. So there will be I to k, and the second segment starts from k plus 1 and ends at j. So in this way, we can go for establishing the formula. I'm not going in detail of it. So actually, it looks like minimum of m of I to k plus m of k plus 1 up to j plus cost of multiplying them together. That means I to k and k plus 1 up to j. The cost of multiplying them together is nothing but pi minus 1, because as the first one starts from I, its dimension should start from I minus 1, like ai starts from pi minus 1 into pi. The same concept here, p of I minus 1 into pk into pj. Okay, if I less than j and minimum of, here the values of k actually lies in between I and j. K starts from I and ends at j minus 1. So here m of ij values gives the cost of optimal solutions actually to the sub problems, but they don't provide all the information we need to construct an optimal solution. So another matrix is required that is called S matrix, S of ij. We will introduce it. That will help us to do so. That means S of ij provides the value of k. Actually, it provides the value of k at which we split the product of ai plus 1 up to aj in an optimal parenthesization. So another table is also required that is not mentioned in the formula actually. We will introduce it at the time of solving this problem. So students can refer my video, which is already uploaded in my YouTube channel regarding matrix and multiplication problems numerical. So my request to all of you to go through this video for better understanding of the solution of a particular matrix chain problem. But for the time being, let us introduce one very simple problem that is I have given here, A1, A2, A3, and A4. So we have to have two tables where we'll store the intermediate results, and from that table we get the final results. As we have the 4 matrix, then we should have construct 2 tables. One table is to hold the cost of multiplication, that is called M table, and another table is to store the optimal value of k, for which we get the minimum cost, that is S table. Okay. So both the table is of having the dimension. Here it is n cross n, and for the time being, assume it is also n cross n. Later on, you will find that it is actually n minus 1 cross n minus 1, because n cross n is not actually required here. So here the first row, second row, third row, fourth row. Okay. Then first column, second column, third column, and fourth column. Here also 4 rows, 4 columns. 1, 2, 3, 4. 1, 2, 3, and 4. This is I, this is J, this is I, this is J. Then how to solve it? Then how to solve the problem? So I told you the first part, if the matrix n consists of only one matrix, and this situation may happen for almost all the sub problems. So dividing into sub problem, then sub problem, sometimes you will get one matrix alone in the sub problem, another matrix alone in the sub problem, A3 alone in the sub problem, A4 alone in the sub problem. So there is a possibility. So A1 actually indicating M table 1 to 1. M of 1, 1 actually holds actually A1. Okay. So A1 means you have a one matrix 1 to 1 in the M table. So for the first matrix, only one matrix, there is no cost of multiplication. That's why it is 0. So if you have a chain consists of a single matrix A2, so in the M table, it is actually 2, 2, M of 2, 2, 2 to 2. The chain consists of 2 to 2, I to J, where I is 2, J is 2, only single matrix. Here I is 1, J is 1. Okay, 1 to 1, M of 1, 1, M of 2 to 2, no cost because single matrix. Here it is I is 3, J is 3. You follow these constants, I equals to J. Okay, so here it is 0, here it is also 0. Okay, fine. So then we have to fill up this one. So what is the value? M of 1, 2. So M of 1, 2 actually indicates you have the chain consists of A1 and A2. This is I, this is J. Then you have to fill up M of 2 to 3. So it is actually A2 and A3. These two matrices to be multiplied. This is I, this is J. Then you have to fill up M of 3, 4. So actually you are multiplying the sub problem A3 and A4. Okay. And the formula says M of I to K, K plus 1 up to J, Pi minus 1 into Pk into Pj, and K starts from I and ends at J minus 1. So here I is 1, J is 2. So K starts from I, that is 1, and ends at J minus 1, that is 2 minus 1, that is 1. So 1 to 1, K has the single value here. So here also 2 to, this is I, sorry, this is I, this is J. K starts from I, that is 1, and repeat up to J minus 1. I'm sorry, K starts from I, that is 2, and repeat up to J minus 1, that is 3 minus 1, that is 2. 2 to 2, that is a single value of K here applicable. The same logic is applicable here. So, sorry, so K here starts from 3 and ends at 4 minus 1, 3. So K has the single value. So whatever value comes in here, the corresponding K value needs to be stored in the same cell number of S table. So actually, S of 1, 2 will receive 1, S of 2, 3 will receive 2, and S of 3, 4 will receive 3. That is the appropriate K value for which you are getting the multiplication value here. That is the cost of multiplication here. So similarly, you have to then fill up M of 1, 3. M of 1, 3 means you are considering the chain A1, A2, and A3. I to J. So here I is 1 and J is 3. So K starts from I, that is 1, and repeat up to J minus 1, that is 2. So K has two probable values. One is 1 and another is 2. So for K equals to 1, you have to apply this formula. Okay. Then K equals to 2, you have to apply this formula, the same formula. Then compare for which K value you are getting minimum. So minimum value must be stored here. An appropriate K value for which you are getting the minimum cost should be stored here. And similarly, M of 2, 4, you need to fill up, for which you have to calculate, take the chain A2, A3, and A4, 2 to 4. So here I is 2, J is 4. So K starts from 2 and repeat up to 4 minus 1, that is 3. So two probable K values, one is 2 and another is 3. So you have to apply the same formula for K equals to 2 and K equals to 3 and store the result, which is the minimum one. So appropriate k value for which you are getting the minimum one, that k value should be stored here. So the final one, actually M of 1, 4. M of 1, 4 means A1, A2, A3 and A4, A1 to A4. So which is the final chain. So M of 1, 4, this value is the result. That is the cost of multiplication, because here you are getting the full chain. The other cells indicating that you are getting the sub chains, but your objective is to solve the full chain. That is the full or the main chain. That is the final chain result. So this one is ultimately give you the final result. So here k starts from 1, that is I, and ends at j minus 1, that is 3. So here k has 3 probable values, 1 up to 3. So 1, 2 and 3. So for k equals to 1, you will apply the formula. So for k equals to 2, you will apply the same formula, and k equals to 3, you will apply the formula based on the observation you got. For the minimum one, minimum value should be stored here, and for which you are getting the minimum ones, that k value should be stored here. So if anybody can solve this problem, so they are expecting the result as, so I have the value here. So the final result, let me write. So let us go for the next slide. So let me write the problem again. A1, A2, A3 and A4 with the dimension 2 cross 3, 3 cross 4, 4 cross 5 and 5 cross 6. The M table value, that is 4 cross 4. Only we are using the upper triangular half, considering from principal diagonal, because the formula says I less than j. Principal diagonal, apart from principal diagonal, if you consider the upper half, here it is 1, it is 2. So I less than j. Here it is 1, it is 3, I less than j. Here it is 1, it is 4, I less than j. So the final value which I have already calculated, here it is 24, here it is 60, here it is 120, that is 64, that is 150, and the final result is 124. And the S table, which is also n cross n, but actually n minus 1 cross n minus 1 is utilized, that you will be able to know here very clearly. The diagonal principal is not getting any k value, because principal diagonal value here it is 0. 0 means no cost of multiplication. So there will be no trace of the value of k. So this part is not actually required here. So 1, 2, the value of k that I told, it is 1, it is 2, it is 3. After calculation, it is found k equals to 2, for which you are getting 64 as a minimum value. Here k equals to 3, for which you are getting 150 as a minimum value, and here k equals to 3, for which you are getting 124 as a minimum value. So the final cost to solve the chain problem is 124. Then the question is, sir, how do you parenthesize them? This is very vital or very important part of it. So actually, we have to call S table where the optimal k value is stored, and here it is I, here it is j. So at I equals to 1 and j equals to 4, M of 1, 4 will give you the final result, that is 124. Here actually it is M of 1 comma n always, where n is the total number of matrices. So S of 1 comma n is getting the last value, that is S of 1, 4 is getting the last value, which is 3 here. So one recursive very interesting definition is there. We have to call S table. We have to call I and j, that is the index of row and column, which is initialized or which is called with the value of I is 1 always and j is n always, because at the cell number 1 comma n, you are storing the last value of k. So here it is 1, 3, fine. The relationship says if I not equals to j holds, there are two subroutines, recursive call actually. One is S, I, and take the value from S of ij. And second one is S of ij plus 1. So, comma j. Actually, S of ij will give you some k value. And here it is k plus 1. And you are getting the formula I to k, k plus 1 up to j. I to k, k plus 1 up to j. The same formula is coming back. So now let us make the parenthesis I comma j. Here I is 1, j is 3. So s 1 3. We are getting the first call s comma 1 comma s of 1 3, and the second call is comma s of 1 3 plus 1 comma j, that is 3. So what is the value of s of 1 3? S of 1 3 is nothing but 2. So it is actually s comma 1 comma 2. So it is definitely s comma 3 comma 3. Okay. Yes, s of 1 3. S of 1 3. Fine. Oh, I'm sorry. Here it j means 4 actually. Sorry. J here it is 4 because n is 4 here. This one. J is 4. So n is 4 here. 4 matrices. 1 4 1 4. Last cell. So very sorry. Here it should be 4. This is 4. So s of 1 4. Yes. S of 1 4. S of ij. That is s of 1 4. So s of 1 4 plus 1. So it is 3 plus 1 4. Here it is s of 1 4. It is 3. So it is 3. It is 4 comma j. Comma j means actually it is 4. So 4 comma 4. So I is 1, j is n. N means that is the ith row, jth column where the last k value is kept. That is 1 4. So actually it is the m of 1n, s of 1n. N means the number of matrices. Here it is 4. This is 1 comma n actually. So s of I, s comma I comma j, that is s1, and j should be started with the value of n, that is 4 here. So now it is 1 2 3, and this is 4 to 4. What it is says? 1 2 3, first matrix up to third matrix. Then 4 to 4, fourth matrix to fourth matrix. This is the simple. Then you take s of 1 3, because here I equals to j comes, no further split, but here there is a chance of further splitting. It is I, it is j. Recursively, it is following this formula s comma I comma s of ij, that is s of 1 3. Then s comma s of 1 3 plus 1 comma j, j means 3. So s of 1 3 is how much? That is 2. So it is 2, it is 2 plus 1, that is 3. So it is 1 to 2, then 3 to 3, 1 to 2, then 3 to 3. So if you further split it on, you will get s comma 1 comma 1 to 2. 1 to 2 is nothing but 1, and you will get s comma 2 comma 2. That is very simple to understand. So this is basically the chain result actually. So the way that we can parenthesize is very simple. You have to call S table, you have to call I and J. I and J will be initialized. The value of I is always 1, J means always n. N is nothing but the total number of matrices. You start the call from there. If I not equals to J exists, then the formula is S comma I comma S of ij. That will give you the K value. Then S comma S of ij plus 1 comma J. Then you proceed accordingly unless and until I and J become similar. So if you get the first call as s comma 1 comma 3, that means first matrix up to third matrix, there is a parenthesis. Then 4 to 4, that is fourth matrix alone. Then 1 to 3 is further being splitted as per the value of k we get 1 to 2. So 1 to 2, A1 and A2 will be parenthesized. Then 3 to 3, that is A3 separately treated. So A1 and A2 will be multiplied first, resultant needs to be multiplied with A3. The entire result will be multiplied with A4, then you will get the final cost. Okay, and that cost is the minimum cost, which is nothing but 124. So now come to the very important part of discussion, that is called algorithm. So algorithm is very simple to understand if you understand the way to solve the problem. If you know the way to solve the problem, then understanding the algorithm is not at all very tricky, very simple to understand. Suppose we have the name of the algorithm is matrix chain, then order, the way that we multiply them. So let us pass the array P, which is nothing but the array to store the dimension sequence P0, P1, P2 that I told. Okay, first of all, you have to calculate the total number of matrices that I told. It is nothing but the total length of the dimension minus 1. If you have the 5 dimension sequence present into P, that is 5 minus 1 is the 4 is the total number of matrices. Very simple to understand. Then you have to take two tables. One table is M, which is of dimension n cross n, 1 up to n row number, 1 up to n column number. And you have to take another table which is S, which is actually n minus 1 cross n minus 1. How we get it? You just see that the principal diagonal is not required. Here the entire part is not required. So actually you are getting the first value from 1, 2, then 1, 3, then 1, 4. So here the row number starts from 1 and ends at 3. Column number starts from 2 and ends at 4. So actually, other than first 3 rows, the fourth row is not at all being used. So first column is not at all used, second column to fourth column. So second column to fourth column actually means 2 to n, because n here it is 4, total number of matrices. And here it is 1 to 3, that is 1 to actually n minus 1. So 1 to n minus 1, total n minus 1 row, n minus 1 row, and 2 to n, here also n minus 1 columns. So M table is actually getting the value in the cell n minus 1 into n minus 1. So somebody may consider the, I'm sorry, not M table, that is S table. So somebody may consider that the dimension of the S table may be, utilized dimension of the S table may be 1 up to n minus 1 and 2 up to n. These are the two tables that be used to this multiplication, chain multiplication. So now you know that the principal diagonal of the M table is always 0, and principal diagonal means row and column number is same, and you have total 4 matrices and principal diagonal consists of 4 entries. So you have total n matrices, principal diagonal consists of n entries. That can be also represented as for I equals to 1 up to n. Then step number 4 says M of I comma I, because principal diagonal where I and j is same, you can use the same value, that is I comma I, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. That is initialized as 0. Very simple. Then step number 5 is very vital to understand. So once you complete the principal diagonal, then you will be going to store the result at M of 1, 2. Then you are going to store the result M of 2, 3. Then you are going to store the result at M of 3, 4. So M of 1, 2 means you have A1 and A2, 2 matrices in the subchain. M of 2, 3 means you have 2 matrices A2 and A3 that I told. M of 3, 4 actually means you have 2 matrices 3 to 4, that is A3 and A4 actually. So here the length of the subchain which you are solving is 2. You are taking 2 matrices. But when you are storing the value at cell number 1, 3, that means you have 3 matrices A1, A2 and A3. Whenever you are storing the result at 2, 4, that is you have 3 matrices A2, A3, A4. So here the length of the subchain, here it is 3. And here the length of the chain is 4. In this way we are going further. So here after the principal diagonal we have to solve a subchain of length 2. Then after completing it, we have to go to solve the subchain of length 3, and then subchain of length 4, subchain of length 5, and so forth. So under that length, we have to identify row and column number, calculate the value by applying the formula, and store the result. Very simple. So this part is actually telling about the length of the subchain, or even going to the solving the main chain, which starts from length equals to 2 up to n. Okay, so here L is the chain length. Chain length. So when you are at M of 1, 4, M of 1, 4. So in that case, you are actually taking the full chain A1, A2, A3, and A4. And the full chain consists of n number of matrices. So that's why it is told chain length starts from 2 after principal diagonal, then chain length will be 3, then chain length will be 4, chain length will be n. So for each chain length, you have to apply the formula, you have to identify row and column number, and you have to solve accordingly. So this part is for calculating the row number, and you find it for every chain length. It may be 2, it may be 3, it may be 4. The first value is always stored at cell number 1. That is cell number 1, comma 2, then 1, comma 3. That means row number 1, column number 2, row number 2, column number 3, row number 3, column number 4. Chain of length 2 complete. Okay. Then here it is chain of length 3. But the first value is stored at row number 1, column number 3. Row number 1 for every chain length for every chain length beginning is fixed. Whenever you introduce one chain length for solving, then every time the first value to be stored at row number 1, then the column number will come. So that's why row for every chain length, row number I will always start from 1. Okay, and it repeats up to n minus L plus 1. This is my request for all the students to verify. That is the the value, that is n minus L plus 1. This relationship you can find it. So for every I, you have to calculate j, otherwise you cannot find it out, that column number, and the formula of j is actually I plus L minus 1. How it comes, you can easily calculate. Suppose you are solving chain length 2, I starts from 1. So 1 plus 2, that is 3, minus 1, that is 2. So I1 J2. So this cell I1 J2, 24. Then I2 J3. How it comes? To go back. So I is now 2. 2 plus 2, 4, minus 1, 3. I2 J3. In this way, you can find it out, the different values of I and J. So the next part is also very vital. So initially, m of ij, for which you are calculating the value, is filled up by infinity, which is a big value. So 24 here needs to be compared with infinity. 24 will be found minimum. The minimum value will be stored. But whenever you are getting 64, 64 is not the first value. For k equals to 2, you are getting 64. So for k equals to 1, there was another value. So the first value needs to be compared with initially infinity. Then that was the minimum. Then current minimum needs to be compared with the next value. Then you are getting the final minimum and so forth. So 124 is for k equals to 3. So for k equals to 1, there was another value. That value needs to be compared with infinity, because initially m of 14 was initialized as infinity, that is m of ij. Infinity needs to be compared with the first value. Then after comparison, that value other than infinity is always less than infinity. That value is taken. Then this value needs to be compared with the next one and so forth. And finally, the minimum value is being stored. Whenever your problem is to minimize something, then the initial value that should be infinity or maximum, then that should be compared. Okay. So that's why m of ij is initialized as infinity. Whatever values comes after computation, that's to be compared with infinity, and definitely that will be the current minimum. If for another k value, you will get another value that needs to be compared with the previous minimum. If this one is the least one, then the new minimum will come out. Otherwise, we will go for getting the remaining part. Then after that, we are applying the formula. Formula means for k starts from I and repeat up to j minus 1 that I told, do, then 10, you have to write the formula. Formula is very simple. M of I to k plus m of k plus 1 to j, sorry, this one nothing, plus p of, sorry, p of I minus 1 into p of k into p of j. You store the value into, suppose, q. For k equals to I, you store the value into q. For k equals to I plus 1, you store the value into q. In this way, once for a particular k value, you get the value and store into q, then that q needs to be compared with m of ij. Initially, m of ij is infinity. For a particular value, suppose k equals to 1, provided the value of I1, you are getting some value and store into Q. That Q needs to be compared with m of ij. If that Q is less than infinity, obviously, then that is the current minimum. Then you apply the next k value. You repeat the formula and store the next k values formula after applying the formula into Q. Then that Q needs to be compared to the earlier value of m of ij. In that way, you will go for finding the final result. So after Q, step number 11 says, this is definitely under for loop of K. If this is definitely under for loop of K. If Q, so far obtained, is less than m of ij, then 12 says it is under if m of ij will be replaced by Q if Q is less than m of ij. And we told for which k value you are getting m of ij is minimum, then that k value should be stored into s of ij. Okay. For k value, for which k value you are getting m of ij as a minimum, m of ij's value is minimum, then that particular k value should be stored into s of ij. So step number 11, if block starts, and step number 12 and 13 is under if block, and Q calculation, that is step number 11, 12, I'm sorry, step number 10, 11, 12 and 13, all are under K loop. K loop is under I loop. I loop is under chain length. For every chain length, you have to solve the sub problems, sub problem, then next sub problem. In this way, you will find out the solution of the full chain. Okay, fine. So this is actually the matrix chain multiplication result. So step number 14 is a separate step. It is nothing under inside any loop block. You have to return. It is a symbolic return M and S. This is what actually matrix chain order algorithm. So again, I am saying that this is one part. Another part is parenthesization part. Suppose we have to write print optimal parents. The formula that we have used to get the parenthesis, we have to call a stable I and j. I always starts from 1 initially and j starts from n, where n is the total number of matrices in the chain. So if I equal j, you are getting only one matrix, then you have to print it. Print that matrix. This is the stopping criteria. A of I, you have to display. Otherwise, that means else, you print the parenthesis open. That means you are dividing the problem into sub problem. S of ij, S, S of ij plus 1, j. This part needs to be under else block. Under else, you call the function recursively that I told, print optimal parents. Then for the first one, S, I, you have to call S of ij that I have already used. The next call is very simple, call the same thing. Then S, S of ij plus 1, it is not j plus 1, S of ij plus 1, j. Then finally, as you have opened it, you have responsibility to close it. So last print, you have to give the print statement, that's print. What we have is expecting is very simple, that is closing parenthesis. So this part will help you to divide it. I to k, then k plus 1 to j, this one. That is A1, suppose A2, and then A3, then this is 1, 2, 3. Then suppose it is 4 to 4, then A4. So then again, there will be a split A1 to A2, though I have shown it earlier. So in this way, this part is actually obtained. So actually, these two blocks are very important to get the full explanations of full explanation of the algorithm of matrix chain. If somebody uses only the first part, he or she can able to get the minimum cost, but unable to form the parenthesize sequence. For it, anybody needs to call the print optimal parents function. This will help us to go for the parenthesize sections. So this is what all about matrix and multiplication. So I think you have understood it. Study it well. The reference is Foreman. Foreman is a very good book to understand matrix and multiplication. You may follow one video which I have uploaded. That is a numerical on matrix and multiplication. Before before going through this matrix and multiplication algorithm, you better to solve one problem. Before solving the problem, you go through Foreman or wait for my next video where I have a plan to explain how the formula is constructed. That is for derivation of the formula of matrix and multiplication problem, how I to pk plus 1 up to jp I minus 1 into pk into pj come. So you just wait for a while to get this video. So after getting this video, you may follow this video first, then you go for another video which is actually telling about the, which is actually expressing the numerical problems on matrix and multiplication, which is already uploaded, and then you go for following the last video, which is currently I'm recording. So in this way, you can understand the full part of the matrix and multiplication. Thank you.